Good morning, fancy meat computers. Welcome back to being at school instead of being on vacation. I apologize for my my microphone not being the good microphone today. I have not yet been able to figure out what the heck the problem is. To be fair, though, I haven't been working at it too hard because I do have a backup microphone that is currently working, so, you know, it's not a game-breaking bug, but, I don't know, maybe I need to try, I don't know, it's tricky. There is a kernel update, and one of the things that you're always praying for when you have a Linux system is that the kernel update will somehow fix all of the driver problems you've been having magically. I've already had that. My secondary screen was I had to update to a newer kernel version to be able to get that working. But anyway, enough about computers. Let's talk about computers. How is everybody? How was your break? Starting poll. How was break? Yes? No? Gorgeous. Or hellish. There we go. Bop. Do I have an NVIDIA GPU? I believe it's an NVIDIA, yes. It was meh. I should have put meh on there. I guess no is you didn't get a break. No break, only maths. Yes, mathematics is your if you're in the computer science program, then mathematics is your constant companion and also a cruel mistress. But yes. Well, anyway, we actually do need to get a move on with this lecture material, so yeah, a system. I should get a System 76 system. Is that a reference to like Fallout 76? Did less reading over reading week than might have been. Yeah, that seems to always be the way. It's like it's called reading week, but you never seem to do much reading on it. I don't know. The midterm term average last year was 57. Yeah, it's not, at that point, it's not even a matter of beating the test, it's beating your classmates. But, yeah. Anyway. So. Let's do it. So, you might have to remind me, because we were talking about the make change problem, I believe. We may have done an implementation of it. I don't recall if we did an implementation of it or if it was just Oh, capital LS, jeez. I don't remember if we actually did the make change problem itself, so you'll have to remind me. Well, anyway, so we were going to do an example. A problem-solving example called the make change problem. The general idea here is that you have a target value, and yeah, I'm pretty sure we did an implementation of this. I'm pretty sure. So, anyway, in the interests of keeping moving, I'll describe the problem. We have a series of coin denominations, and we have a target value that we want to hit. We want to choose coins which make the smallest change possible. So, you know, solving the make change problem is trivial if you like. This is an interesting problem because it's an example of a problem that has different strategies, right? So part of the issue with the make change problem is we have to decide which strategy is the strategy we prefer. We have to develop some kind of means of selecting between the different strategies. For example, the easiest strategy for the make change problem is to just take the smallest coin value and divide the target value by that, and that'll give you how many coins you can make change in the smallest coin denomination with. Yeah. I got to compute every possibility and pick the smallest change among them. No, that sounds like a dynamic programming algorithm. But, yeah. So that's a trivial strategy, right? It will give you a result, but if you were to think of it as an actual real-world situation, that would be a terrible strategy for, you know, your cashier at the MoMac cafeteria to just give you your change entirely in pennies, even though pennies don't exist anymore. So we have this sort of implicit assumption that a good solution to the make change problem minimizes the number of coins which you have to use. Yeah, knapsack. Yes, yeah. We are talking this. So, some people in the chat who are computer whizzes understand that we're heading in general knapsack territory. Knapsack problem is a different problem. It's also in the same class of problems as the make change problem, but you can talk about that in your algorithms course. So with respect to this one, to the make change problem, one possible strategy for making change is to take out as many of the biggest coin as we can until we can't take out any more. Then we move on to the next biggest coin, take as many of that out as we can until we don't have any more, etc., and keep track of how many coins we took out of the total each time. This is what's known as a greedy algorithm. So the greedy algorithm is a variant of a general problem-solving strategy which you probably won't hear about until at least second year. But it's called a matroid. Hey, Mark, have you done matroids yet? Tell me if you've done matroids yet. You're in third year now. But anyway, greedy algorithms are a type of a matroid type problem, and it's not Metroid. We're not going to be shooting Metroids. We're going to be it's Matrixoid, Matroid, not Metroid. So yes. So the idea with a matroid is that you have a problem. You can make a decision about the problem, and that results in... No, is that third? Yeah, okay. Next semester. Okay. Well, here's a quick intro. So, if you have a problem, you make one decision about a problem, and that resolves it into a smaller problem. It's the same problem, but smaller, right? So with respect to the greedy algorithm, the make change problem, we have a target value, we have a set of coins. If we make a decision about how many of this specific denomination we can extract, we can calculate a new total, which is smaller, and we have a new set of coins, which is smaller. So long as we're keeping track of the decisions that we make, we are presented with exactly the same problem, precisely the same problem, with a smaller number of things to operate on. This is what's known as a matroid. It's like you have a problem, you have another way of thinking about it is you have a space of possible solutions to the problem, right? Each decision that you make about the problem reduces the size of the space of possible solutions to that problem. And you reduce the space of possible solutions until you have one solution. That's another way of thinking about it. So this is getting into some pretty, highly advanced territory. But fortunately, the make change algorithm itself isn't that difficult. It's not that difficult to understand. How is that different from recursion? Well, that's a very good question. Thank you, Arian. So recursion is a method of solving a problem, but it's more general than just matroids. So what a matroid does is it allows you to define a problem recursively. Like we could easily come up with a recursive algorithm which implements the make change problem here, because we've defined it in such a manner that, you are solving iteratively smaller versions of the same problem. This is one of the great strengths of recursion, is that it applies itself very easily to these types of abstract, these slightly more abstract problems, right? Yes, you would use recursion in a matroid, but you can use recursion in much more than just matroids. It's a more general technique. For example, I won't describe I'll name a few algorithms, but I won't get into them because we have to keep moving. Merge sort is a divide and conquer algorithm, so not quite a matroid. It's different from a matroid, but it's still using recursion. I think quicksort is a divide and conquer algorithm as well. Yeah, anyway. So this is the make change problem. We have our target value and we have our tuple of coins. The first thing we do is create a dictionary that is blank. We then use a while loop to iterate through the different coin values. So we start at the end and go down to the beginning. Notice that we are going by we're subtracting 1 from I each loop iteration, but we say that the particular coin we're dealing with is whichever element of the array. We get the number of this coin that fits inside of the target value using integer division. The result array gets loaded with that information. Then the target value gets reduced by that coin value times the number that we removed. And then we iterate through that until we run out of coins, and then we return the result. So this is the make change problem. That's a greedy algorithm. So remember that the thing we wanted was to reduce the number of coins that we're giving out. So you can think of this as a minimization problem. Some of you may have. I saw some complaints in the chat about. I think probably a calculus test that you guys have coming up. Can I explain one more time? Where is the greedy algorithm part in the given code? So it's not like you'll just like call a function that says greedy, right? The fact that like the fact of this being a greedy algorithm is contained in the idea that we are starting with the biggest and most obvious decision, making a decision about that, and then moving on to the next most obvious decision. With respect to the make change problem particularly, the largest coin denomination is going to be the one that's, most likely to be upset if you don't deal with that one first, right? So we start with the biggest coin and we move down to the smaller ones. The fact that this is a greedy algorithm is implicit in the structure, but it's also implicit in the problem. So we're going to give me a moment because we're going to talk about why this is a harder problem than it looks like at first. So our greedy algorithm. The question is, given that our criteria for effectiveness of the algorithm is, does it return the minimum possible number of coins, right? You can think like. If you think of this in terms of calculus, you can think of each different particular type of algorithm, being a, points on a graph, and you're trying to find the minimization of that function, right? So it's not quite the same thing, obviously, but we are trying to minimize the number of coins. So consider the following situation. What if our target was 14, and the coin set is 1, 5, 7, 10. Now, that might seem like a stupid way to arrange your coins, but if any of you have ever been to Europe, it's kind of interesting because, like, the euro, like, it's amazing how many euro coins there are. Like, there's like a 1 cent piece, a 2 cent piece, a 5 cent piece, and a 10 cent piece, a 20 cent piece, a 25 cent piece. It's like there is a large number of different coins in euros, and like this doesn't look like the sort of North American standard for coins, but there are coin systems that look like this. So the optimal number of coins, sort of just looking at it and using our brains, is that you would have 2 7-cent coins, right? However, our greedy algorithm starts with the top and moves down, so it would assign 1 10-cent coin and 4 1-cent coins. That's 5 coins in total, which is non-optimal. That is deeply suboptimal. So, it is a fact. The greedy algorithm gives optimal results, assuming that each coin is at least twice the value of the previous coin. If that's not the case, then you're not going to get the optimal number out of the greedy algorithm. So this makes this problem hard. In fact, in computer science, we call this a non-polynomial algorithm, or it's non-polynomial hard. That's going to make more sense once we talk about big O notation in a little bit. But essentially, NP hard or NP complete problems they're kind of the white whale of computer science. Like in the Moby Dick sense, there are tons of Captain Ahabs trying to spear this problem, but nobody's quite managed it yet. Everybody who's tried has had their ship sunk, and all of their crew died. But so when we talk about algorithms, we can classify algorithms by the complexity of the algorithms which solve them, right? Or we classify problems by the difficulty of the algorithms that solve them. So the problem with non-polynomial time algorithms, in order to solve this problem, you would need an algorithm that does look back, right? You would need to calculate a number of different results and then select the best one, right? As opposed to just being able to do an iterative algorithm that is guaranteed to produce the correct result. Because it's just something, like, it's a quality inherent in the problem that you can't do a single pass, straightforward algorithm that finds you the correct result every time. There are various ways of dealing with this. Sometimes we sort of constrain our idea of optimality. We modify what we consider optimal, or we're like, well, if we don't have the best result, perhaps it's good enough to have a good enough result, right? A good enough algorithm that's much faster can be, in some cases, preferable to an exact algorithm that takes a lot longer. But it's inherent in the problem structure that in order to find out that 2 7s would be the optimal solution here, we would have to be able to calculate several possibilities and compare them. That increases the number of times that you run this algorithm by quite a bit. And there are various algorithms, like various general algorithms that you can use to solve these types of problems. One is called dynamic programming. But again, this is something that you'll see in third year. Are pathfinding algorithms the same? I believe so, yes. So pathfinding algorithms are an entire field of study in and of themselves. But if you're talking about a maze-solving algorithm, a maze solving is kind of like a subset of pathfinding algorithms. So think about how you solve a maze, right? If you're like a 7-year-old doing a maze on paper, right? What you do is you have your pen along the paper. You look down the paths and see which ones result in dead ends. And then you don't take the ones that follow the dead ends, right? So you are looking ahead, right? The problem is when the computer looks ahead, it takes time for it to do so, right? So when you're solving a maze as a 7-year-old, you're using something approximating a dynamic algorithm, because you're looking ahead and only keeping, like, you're keeping track of previous results and referring back to them if you hit a dead end and that kind of thing. There's backtracking. The wrong way to do a maze is to actually trace your pen into every dead end, right? But your eyes are going to be doing that anyway. So yeah. Oh, you mean shortest path algorithm, something like Dijkstra's algorithm. Ask me when I teach an algorithms course. I'm pretty sure Dijkstra's algorithm is, I think it's greedy. I think it's a matroid. I think it might be a matroid. I'm not sure, though. Don't quote me on that. I raised the pitch of my voice very high there to indicate my level of not knowing what I was talking about. So, very good, very good. Let's move on. Functions and recursion. So, we're going to talk about functions. We're going to talk about recursion. It's going to be fun. So, good. So, functions. According to Wikipedia, it's greedy. Aha! There you go. Thank you. Thank you, Jason. So, again, for most of you, you don't have to worry about that. But if you're in the comp sci stream, that was just a preview of coming attractions. So, oh, I forgot to explain, though, why NP hard problems are the white whale of computer science. A proof or an algorithm which solves NP hard problems in polynomial time. Basically, this is like the holy grail, of computer algorithms. If you found an algorithm like that, you could break all existing encryption. If you found an algorithm like that, well, most existing encryption. If you found an algorithm like that, you would be able to, like, it would just blow the lid off of what is currently possible in terms of programming. we would suddenly, like, be, like the computation would just, like, it's like one of those things that's preventing computers from being as smart as humans. If you were to blow through that barrier, you'd be much closer to, like, computers with human levels of intelligence. But anyway, so the problem, of course, is that nobody's been able to do it, and they've been trying for a very long time. But there's no proof that it can't happen. So it's kind of interesting in computer science because you can have proofs that things are impossible, but when it comes to P versus NP, there's no proof that it's not possible that some hypergenius, at some point down through the annals of human history, way in the year 2525, some hypergenius comes up with the solution to P equals NP, and therefore computers just break everything. Computers become reality. But yeah, AI is looking sus. Doesn't the AI always look sus? So yeah, that's the reason that you hear a lot about P equals NP. Like, you'll see occasionally around the department people wearing T-shirts that say P equals NP, I believe, because it's kind of taken. You kind of have P equals NP theists versus atheists at this point, like people who don't believe it exists and people who believe it exists. It's just out there somewhere. We haven't yet been able to grasp it. But anyway. So let's talk about functions. Functions. You should be using them. You should have used them quite a bit by now. You use a function to group together the commands of the language, package them up into a tight little ball so that you can throw them into different parts of the code. This is an abstraction mechanism. Good. Syntax of functions, you should already know that, so we won't dwell on it. Function parameters. So this is an important piece of nomenclature, actually. So, oh my God. If you want your slides redone, do it yourself. Yeah. So, this is what's going on here. This is an important piece of nomenclature. The function parameters that you include in the declaration line of the function itself, those are known as the formal parameters. The function parameters that are provided while calling the function, these are called the actual parameters. How is abstraction used in function definitions? Function definition is abstraction. Yeah, looks like my slides might need a touch-up. You're telling me. It takes a lot of time to fix slides, because I know if I got started fixing these slides, I would just have to end up completely redoing them, and I can't it's physically impossible for me to do 2 sets of lecture slides in one semester, and right now 3MI3 is getting all of that attention. So yeah, unfortunately, the slides I got are the slides I got for the time being. Sorry about that, folks, but it is what it is. So it's important to understand the distinction between the formal parameters and the actual parameters. The actual parameters get assigned to the names of the formal parameters when the function is called. This is called pass-by assignment. It's a style of pass-by value, which is, how C passes out things into functions. But, yeah. So, everything, like all of the tricky little bits about assignment that we all know about now, having done, if you remember all of the aliasing stuff, aliasing happens because of assignment. Python functions use pass-by assignment, so if you pass a list into a function, you create an alias to that list outside the function. This is why it's a bad idea to modify the parameters to a function inside of the function. You should usually declare a separate variable. Yeah. There you go. So, interesting little bit about functions, you can actually give them default values, or you can give parameters of function default values. This is kind of a cool thing in Python. I don't like Python as a rule, but this part of Python is pretty okay. So, when defining a function, you can provide default values for function parameters. You need to have parameters with default values after all parameters without default values. So if you are, it's important that you place these positionally. When calling a function, you can omit optional parameters, which will then be assigned to the default value. So, demonstration. So, let's say I had a function, quick little function, add 3, x, y, z, return x, shallow copy, go brr, yeah. There we go. Nice, quick little function. Add 3, 1, 2, 3. There we go. Let me just print that, because I always forget to. Tab. There we go. Python 3. Topic 5.py. So the answer is 6. Surprising no one. So to use a default parameter, all you have to do is put a little assignment statement inside of your function declaration line. So if I say z has a default value of 0, I can omit the third parameter, and you can see that it just adds 1, 2, and 0 now, right? It's performing the same addition, but it's substituting 0 for z because we didn't specify a z. Now, limitations to this are that you can't have one of these in the middle. Or can you? Maybe you can. Did I save it? I didn't save it. There you go. Yes. Non-argument follows default argument. So you have to, if you're including default arguments, they all have to be stacked up at the end of the function declaration. There we go. And there we go. There you go. So the other thing that's interesting that you can do here is you can assign so inside of a function call, you can specify which argument particularly you want to use. For example, z is equal to 7. There we go. Is there a reason why someone would use that over just defining a local variable? Is there a logical reason for this behavior? There's a logical reason for all of the behavior. Yes. So I'll show you a practical example of this. In the GHCI interpreter, sorry, Python 3. I've been doing some Haskell lately as well. So, help print. Help print in braces. So you'll see that print has a bunch of these default, or these optional arguments with default values. So it's kind of interesting, right? So if we print hello world, right? That just prints hello world. If we say the end is equal to new line, ta-da, new line, then that is the, like, that specifies the character or the string that's appended to your string before it's being printed. Of course, you can throw other things in here as well. And the separator here, notice that the separator is a space, right? So you can also say sep is equal to, for example, tab. And there you can set all of these interesting parameters. You've all been doing Haskell. Haskell is, Haskell is a really good language, but it's kind of like, Haskell as a language is kind of like a fine wine. You won't appreciate it until you've developed your palate. The only good thing about Haskell is the pattern matching. Try the type system. Try the strong static typing. Try function application as spacebar, because that's how much you use it. Try currying. So, thank you. So, let's talk about scope. Don't be a dope. Remember the scope. So, scoping is a very general concept in computer science. I have one question about default arguments. Why can a default argument be only followed by a default argument? I don't know. Because that's the way Python does it. Probably otherwise it confuses Python. So, scoping. Scoping is a very general concept in computer science, and a very important one to get down. There's an easy way to think about this and a complicated way to think about this. The easy way to think about this is as a binary. It's like yin and yang, right? You have global variables and you have local variables. Global variables are applicable to everything in your program. A local variable has its domain restricted to just the function that it's defined in, right? So, so if I were to define a global variable, I would say something like x is equal to 9, right? X is equal to 9. I can use x inside of this guy, right? and everything should... there we go. X is equal to 9. Everything's fine and works. Lots of stuff going on in the chat. So, the scope of a variable, if, like, in general, no matter whether it's a local variable or a global variable, the scope of a variable is always that part of the code after its first use. Is it the same as declaring a static variable in Java? I think so. Global variables, static variables. See, the thing about these sorts of things is each language is going to have slightly different rules about how they scope their variables. So it's like global variables and local variables are general categories that will apply to most languages. You know, how that is interpreted in any specific language, you kind of have to be familiar with that language to know that, and I'm not familiar enough with Java to be able to answer your question, unfortunately. But I'm sure if you checked the documentation, you'd be able to find that information. So, X. The scope of X is everything past X. The scope of N is everything past N. There we go. So this is computing the factorial with no function. All of the code is at the top level of the program. Once this code is run, we can't call it again with different input, no reuse, no modularity, and all variables are global. So if this is just the script, right, all of these variables are global variables. So, oh yeah, I was shocked and horrified that, like, despite having done 1JC3, like, or despite like half of my my 3MI3 class having done 1JC3, like very few of them actually remembered any Haskell programming on a course that's ostensibly teaching Haskell programming. But whatever. No. It's, far be it for me to criticize any other professor. That would be unprofessional of me. No, clearly, if there's any fault, it's like all professors are pure and spotless, and like pure avatars of mathematics. If there's any part of the courses that we teach that are not absorbed by the students, it is purely the fault of the students being not up to our standards. That's the only thing that can cause students to not learn, is the students themselves not being good enough. So, yeah. So, so scoping. When you've scoped something, when you've declared something inside of a function, the scope of that thing is, like, it is local to the function. That's how we say it. It is local to the function. So this x here does not exist outside of this function. So I've done this example before, but if we print, for example, the value of y here, y being a local variable inside of the add3 function, we get a name error. Y is not defined. Y is not a global variable. We can make it that way. Y is equal to 0. Global Y. This will probably cause a problem. Yeah. Y is a parameter and global. Yeah, so you can't have it be both. You can't have it be both. It has to be either global or local. But that's the syntax for declaring a global and bringing it into a function. So by default, everything that's inside of a function is local to that function. In order to use a global variable inside of a function, you have to specifically declare it global. Yeah. 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 The definition of factorial and print statements are top-level code, but the red lines are local to the function. We can use the factorial function many times with different inputs. Yes. And you'll see that if we try to access these values, we'll get an error. They can't be used outside the function. So, in this case, trying to use n as a global variable, even though n isn't defined when we define the function, n is defined by the time we first run the function factorial. So that's an interesting thing, right? Because you can kind of pop things in and out and down and around. Like if I were to add like a w here, w is equal to 6, declare a global w, we would get, oh, still asking for y. There we go. Everything works. So notice I'm declaring it here. I'm using it up here, but keep in mind that this function definition is only being executed after the declaration of the global variable. If I move this guy down to past our first use of add3, we get a name error, name w is not defined. So this is part of the reason that global variables are generally avoided. Generally speaking, the correct way to approach the use of global variables is to not use them except in very specific circumstances where no other solution presents itself. It is preferable to add parameters to a function rather than use global variables in it. With respect to the functions that we're having you do for the assignment, you'll not really need at any point to add any parameters to them. But yeah. Oh, somebody just plugged Learn You a Haskell. Yes, Learn You a Haskell is a really good resource. Actually, since you guys are all talking about Haskell anyway, I have a I may have shown you guys this link before, but I'll do it again just because I found it to be a very, very good and useful video, so I'd like to share it with you. A series of videos, actually. As a refresher course for 3MI3, I collected up a few resources. So there is, if you just go into YouTube and search these names, these two video names, you'll be able to, pardon me, find these resources. So, Learn Haskell in one video. I found that to be an extremely good video on how to learn Haskell. Lately I've been really into the computer file videos. I don't know if any of you, if you haven't heard of the computer file YouTube channel, Big shout out to Computerphile for being extremely interesting. They go and like actually dig up the graybeards who are sort of now sitting as like professors emeritus in like Princeton University and places like that. They go and they talk to these people, and they they ask them, what was it like knowing the guy who developed C originally and stuff. Can I share the links? Yeah, I'll put it up on... Send me an email. Send me an email to remind me. I'll put the links up on the 1MD3 Avenue page. Or maybe Mark could do that for me. Thank you, Mark. Learn Haskell in one vid. You don't learn Haskell. I mean, yeah. Ever watched the sum of all natural numbers is equal to -1/12? No, I haven't seen that. But yeah. Oh, I have an actual question. Do you have to do function xy is equal to 0, or could you do function x0? Like, do you have to put the name of the default parameter when you pass? Yeah, you have to put the name in. Absolutely. Like, to put a literal there doesn't really make any sense. Like, if I were to add another parameter that was like 4, that doesn't make any sense. Syntax error, invalid syntax. If you need a 4, just use it in the code. Right? If you need a 4, just use it in the code. But, yeah. Okay, well, that is my my time for today. So, I'll be seeing you guys around. If you have any questions, please hold them for tomorrow because I've got to get to my next class. All right. Have fun. Don't die. Don't worry, it's just calculus. They can't flunk all of you. Have a nice day.